Have you ever had this moment where you attempt to 3D print something and then you leave to do other things? And then when you come back a few hours later, you're greeted with something that looks like a mess. We've all been there, and it really does get frustrating, especially when you've waited this long. So, for our Advanced Digital Systems project for university, we are introducing Passive Control, a real-time 3D printing defect detector so you won't ever have to worry about the spaghetti you never ordered ever again. Let's get into it.
Alright, hello guys. Here's my group. I'm Ashton.
I'm Darian.
I'm Austin.
And I'm Lance, of course. And my channel, Lance Bermejo. So, yeah, this is week 2 of our project. So, yay.
So what are the different types of 3D printing defects? And there's actually a few of them. The most common is spaghettification, and the name speaks for itself. This occurs when the new filament does not stick with the old filament. And this is primarily due to bad adhesion, improper bed leveling, too hot or too humid of an environment, and much more. And another one are zits, and they are mostly caused by excessive hot end pressure, improper retraction settings, or moisture in the filament. And another one is strain, which, let me tell you, as someone with a 3D printer myself, this happens to me a lot, and it is not pleasant. Alright, now for our system overview. So, as engineers, we want to make sure to solve these problems as much as we can. And for passive control, our proposed system architecture goes like this. We have the hardware edge node, the AI vision pipeline, the MQTT telemetry, and the end user GUI. So starting with the hardware we used for our edge node, we used the Raspberry Pi as the basis for our node. And the Pi 5 should be capable of running our programs as it allows us to run Python code and use GPIO libraries using the built-in pins. And we could have also used a Raspberry Pi 4, but it would be a lot slower. And for our camera, we used a FreeNav Pi camera, a high-quality camera that is great for detecting 3D printing defects in real time. And for our humiture sensor, we also used a DHT11 sensor to check if the room is either too warm or too hot, and also for checking moisture. And lastly, we also used a 5-volt relay module, an electromagnetic switch that allows our Raspberry Pi to control high voltage/high current devices. And next up, for our AI vision pipeline, we actually used a pre-trained AI image processing model for object detection, which comes from Hugging Face, which is specialized in 3D printer defects. We went with a pre-trained model using massive datasets because that saves us a lot of time, because fine-tuning or training from scratch by feeding massive amounts of data into our machine will just take up too much time. So yeah, that's why we went with that. And this is also accompanied by the YOLO-11 model from Ultralytics for object detection. And we use YOLO because of its speed and accuracy, and all of this will run locally on the edge node to minimize latency and take full advantage of the Raspberry Pi 5. And now for the MQTT telemetry, which is actually the section I worked in. So we use PayHo for our MQTT with an object-oriented design, and this takes advantage of our Raspberry Pi 5 to publish inference images with the confidence score, as well as sensor data to a specific topic on a broker using the built-in Wi-Fi. So how this works? We created a base MQTT client using PayHo, and then extended it into specialized clients. One for the Raspberry Pi, one for the ML detection module, and one for the GUI. All inherit from the parent MQTT class and communicate with each other, though each have their own customized behavior for each component, which results in a modular and manageable system. So why did we choose MQTT, you may ask? It is because it is lightweight and it allows for real-time updates and decoupling. So if you want to know more about how MQTT works, check out Rui Santo's detailed video in the description below. And lastly, for our end user GUI, we used PyQt5 so you can see the data on screen and have control over things. And our end user GUI will remain fairly basic and lightweight, as little to no processing should be done on this device. So it comes with a centralized remote hub, real-time data visualization, and smart defect alerts and notifications. So all in all, you can have as many nodes as you'd like, so you can see it in one computer, like we did here in the screenshot, for example. So, for example, the end user on his laptop has access to the GUI. He can see other edge nodes,
you know, the Raspberry Pis with the cameras and sensors, thanks to the MQTT client, as the broker is our server.
And before we get into our demo, Ashton will show you our detailed plans, so I'll just pass it off to Ashton and he'll give you an overview of what our system will look like.
Lights, camera, action.
So you can excuse the chicken scratch, but the idea is that we've got a camera pointed towards our 3D printer, and then that camera sends images to Raspberry Pi. We've decided that we'll use a Pi 5, so that's going to affect our GPIO calls. In addition to this, we'll have a humiture sensor, so we can measure the humidity and temperature in the room. That's going over I2C, I think, to the Raspberry Pi. From there, there's going to be some machine learning and things like that, but all of the outputs of that are going to go over Wi-Fi to some public MQTT broker, and then that'll be received in a GUI. It's going to be a one-way transaction, so we're only going this way, never that way. As for the software side of things, so we're going to have a few threads. So our camera thread is going to generate the image as we showed, and that's going to be an image of the 3D printer. So and then that image goes directly to the MQTT broker to be downloaded onto the user computer. And then that image as well goes into this machine learning module, which is going to determine whether or not there is spaghetti detected in this system, or in the image.
And this is like the hardest part, pretty much.
Yeah, it's going to be the source of the most significant effort, because everything else is pretty tested technology. It's stuff that you can implement in a day of light vibe coding. But this is this is the tricky part that we'll have to figure out. And then as well, we'll have that humiture sensor sending over humidity and temperature data to that broker, all to go to the GUI, which at this point is kind of abstracted out by this MQTT cloud, but that's definitely not a bad thing. Abstraction is good.
So after we made our diagram, we all split up into our own sections using the divide and conquer approach. So Darian worked on the humiture module, I worked on the MQTT, Austin worked on the camera module, and Ashton worked on the GUI, as well as the ML module. So we implemented, unit tested, and debugged each system until everything's working well. And overall, this project took us a few weeks to do. And at the end of this video, I'll be going over the roadblocks and challenges we faced, as well as the alternative hardware we could have used. And for now, here is our demo after getting everything together.
Up on the top left here, this is just a test script running from what will be running from Raspberry Pi. Right now, it's just a debug script that sends an image over the network. Then that's going to send down to here the machine learning box, and it's going to process the image, see if there's spaghetti in it, detect it, and then send that up here. And this box controls the GUI, which will be down here, where we'll see the temperature, humidity, whether or not spaghetti is detected, as well as an image of the 3D print and a box around any predicted spaghetti. So let's see that in action.
So let's check it out.
I'm gonna hit enter, and then it's gonna go bing, 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 bing.
Chain reaction. Nice.
And notifications too. So if you've got interesting that it doesn't pick it up there, but my hands are in the way. So.
Yeah, it updates slowly because, yeah, obviously. Now let's try to hide it. Okay. Yeah, so at least we know that works. All right. I was wondering if you can maybe stop the power supply now. Let's see if it works.
Should I stop sending now?
Bam, and power supply is off. So we're gonna be using a relay for this one instead of like the LED. Like this is just a test, so. Sweet, all works. Good job, guys.
Good job, Lance.
Woo!
So overall, our project worked pretty well. So it wasn't perfect, of course, but for the most part, it was able to detect defects in real time. But I'll be honest, I don't know too much about relay modules, as I wasn't directly involved in that portion, but it's something I'm interested in learning more about, so it's a topic for another time. And now for the challenges and roadblocks we faced. So I won't be talking about what we debugged for each iteration, as that is redundant.
So one of the roadblocks is actually with the fact that there are a lot of 3D printers out there. So our focus was on extrusion 3D printers, but there are also types of printers such as resin and powder that we didn't focus on. And not only that, there are also some open consumer and enclosed consumer cases, as well as industrial cases. So yeah. Another roadblock is that there are already existing solutions. However, unlike our open source solution, they are centralized and closed sourced, and they actually acted as a source of inspiration.
But the biggest challenge we faced is actually with tuning our model. So, according to Austin, initial results only showed 75% accuracy, and that is pretty low. But thankfully, we were able to get that up to 99.5% accuracy. So how he did that was actually by increasing the size of the dataset. So by that, he actually fed more data into the machine learning model, so it'll be able to have a better idea on how to detect objects such as zits or spaghetti. As for the alternative hardware we could have used, but we didn't end up using, we could have went with a Raspberry Pi Pico or even an Arduino because it is lower power and it's cheaper and has a built-in ADC converter. But the problem is, it will present us with a lot of challenges because it doesn't run Python natively, and overall, the Pi 5 generally has better camera support. We also could have used a USB webcam as it is portable, but it generally has worse integration with Raspberry Pi software. And lastly, coming from Ashton, we could have integrated directly to stop G-code, but that makes it much more complicated to implement, unlike using a simple relay. And now for improvements for the future. So the improvements we'll take in the future is that we could use a better dataset or machine learning training module. These are topics for another time, and it's something we'll consider if we so choose to continue with this project in the future. So to close off, we are very happy with Passive Patrol.
This project will definitely come in handy for a lot of consumers who want to prevent wasting time and filament for their 3D printers. And again, there are definitely improvements to be made, but for a submitted project, this is what we have currently, and it's definitely something I'll be using for my 3D printer back at home. So overall, this project demonstrates how IoT computer vision and real-time systems can improve reliability in manufacturing workflows.
And with that, thank you guys very much for watching. If you liked what you saw, please hit that like button and subscribe to my channel for more tech and engineering content just like this. Feel free to leave your thoughts in the comment section below, and I'll be happy to answer. And until next time, I'll see you in the next video.